Now back to the problem. Again, we have our delta S, 0.7 meters times I, minus 0.9 meters times J. And we know that delta S is, well, V naught vector delta T plus 1/2 acceleration vector delta T squared, or in this slightly less compact form that we have here, same thing. So we can set this equal to this. When we then put our numbers in for the acceleration of gravity, the negative 9.8 meters per second squared delta T times J. Now I've done it in this form. We have the acceleration times delta T times J, acceleration of gravity times delta T times J, and we have our V naught plus V naught, and then adding the A delta T here. And then we've got to multiply that by delta T. And that's equal to, well, we simplify it, we get the V naught delta T minus 4.9 meters per second squared times delta T squared times J. Left off the J. Now our V naught is already a vector, but over here we need to have the J. So now we have this equal to 0.7 meters minus 0.96 meters times J. Then we have, let me back up a second here because I think something is a little bit incomplete down here. Let me fix it. Okay, I've added a couple of things that should have been there in the problem as I did it in class. You can't just have a V naught. Well, you can have just a V naught here without an arrow if you assume that V naught is only in the X direction, which is valid in this case because the projectile is said to go off the edge in the horizontal direction. However, I wasn't very explicit about that. I just wrote V naught. I'd have been better off to write V0x delta T equals 0.7 meters, I component equal to I component. But even at that, I've skipped some stuff here. Probably wasn't a good idea to skip. And up here in my initial conditions, I didn't indicate the condition that V naught was horizontal. So, had I started off by explicitly indicating this, which you should do when you do the problem, V naught is V naught x delta T times I. There's no J component because V naught is said to be entirely horizontal. Now, the next problem, we're going to take V naught away from horizontal, and then things get algebraically a little bit messier. If we do this, then let me write something over here. Let me just rewrite what we have here with the explicit form of V naught so we can see for sure how these two equations come out of the vector equation. Now, writing out this equation more explicitly, first I just wrote a copy of the equation. This first line just matches this equation. Try to connect this with this in a way that's pretty much airtight. Okay, so V naught delta T means then V naught is V naught x delta T times I. So we got V naught x delta T I. Then we got our minus 4.9 meter per second squared delta T squared times J equals 0.7 meters times I minus 0.96 meters times J. So that I component equal I component gives us V naught x delta T equals 0.7 meters. I'm having a rash of neglecting to write down simple variables. Now the delta T should be in here. I'll fix that in a minute. That should be V naught x delta T equals 0.7 meters. And then the negative 4.9 meter per second squared times delta T squared equals negative 0.96 meters. And these equations are very easily solved. This one for delta T, this one for V naught x. It appears that I also left the point off of the 0.7 up here. In any case, I've fixed this. It's V naught delta T equals 0.7 meters. So these two equations, again, easily solved for V naught x and delta T. Of course, the delta T, we have a plus or minus, but the minus, I'll just mention briefly, corresponds to what would happen if the projectile had been projected down here and had just happened to be at this point with this horizontal velocity at the same time as the projectile actually left the ramp. So had we projected a projectile here in let's say, in phantom space or something, and it joined up with this one just as this one hit the edge of the ramp with an equal velocity in this direction, then the negative delta t is the time at which it would have been down here. So think about that if you like. The point is that we use these conditions to set up a vector equation which we then solve ultimately by setting I component equal to I component, J component equal to J component. Now, you could do that at the beginning, and of course that's the approach your textbook uses, but putting it into a wider perspective gives you a little more power and a little more insight into the nature of the vectors, nature of vector equations, and that can do nothing but help you as you move through your vector calculus, those of you who are taking it, as most of you are, and into subsequent courses that rely on it.